Welcome back. Today we are going to start with a very important topic. That's what we call as capacitors, or sometimes they are also referred to as condensers. This is a topic not limited to electrostatics. Rather, very good questions in transient current, in chapter called transient currents and alternating currents. You would be able to solve very good questions over there if you have a good underlying understanding of the concepts of capacitors. So let's start with this. A capacitor is a device which is used to store charge. But don't confuse it with other charge storing devices which store charge in the form of chemical energy, like a lead acid battery used in your car or domestically. That's a device which converts charge into chemical energy, and then a reverse reaction produces back that electrical energy to be used later. However, this is not a device which converts electrical energy into chemical energy. This stores charge in very minute forms, yet they play a very important role in, for example, smoothing of motion of a motor, electrical motor, and many more topics. I don't want to go into the details of that right now, but during the continuation of this lecture series, I'll touch those topics one by one. So what is a capacitor? Capacitor is a device which stores charge. It is represented as a circuit element with the help of two parallel lines, and the capacity, its capacity to hold charge, is what we call as its capacitance. You may simply call it capacity as well, and that's why the name capacitor. How much charge it can store is the first problem in hand. How much charge a device can store. But before we jump on to this kind of practically available capacitors, let's start the concept from treating by dealing with the analogy. Let's say two water tank analogy. Let's say I've got two water tanks. This is one and this is another. Let's say they are connected with the help of a pipe, and it has got some water in it. Now I want to ask you, how much water will be stored in the second tank? This is first, this is second. This is the reservoir which is providing the charge, or water in this case, and this is a device which is holding that water. How much water it can hold? You'll say, if the water level in the first tank is too high, the water level in the second tank would also be high, and it will store a lot of charge, a lot of water. What if the water level in the first tank is, let's say, at somewhere over here? Obviously, the water level in the second tank would also be same. That means this time it will hold lesser amount of water. Although it is not technically correct what I am going to show right now, but it is a good way to understand the basics of what we mean by this analogy. Let's say I've got a sphere and I want to store some charge on it. What will I do? I'll connect it to something which is reservoir of charge, which can provide charge to it. Let's say that's a battery, and I'm assuming that it has got unlimited charge. Although this is technically not correct, but just for the sake of understanding, let's say I connect it to this. Let's say this battery is of 3 volts. This battery has got an EMF of 3 volts. So what will happen? This means this is grounded, so this is at 0 volt, this is at plus 3 volt. Now charge will keep on flowing on this sphere. For how long? Till the sphere also don't reach to a potential of 3 volts. So when its potential is also 3 volts, and I am assuming that it has its potential is not falling. So when it will also reach to 3 volts, the charge will stop flowing. So how much charge this sphere can hold will depend upon the voltage, the potential difference applied. Had the level been higher, it will store more charge. Had the level been lesser in the first tank itself, the level in the second tank would also be less. For example, let's say instead of 3 volt, if I give it 1 volt, only a little amount of charge will produce a potential of 1 volt, and this time the second sphere will hold lesser amount of charge. That means how much charge this sphere can hold depends upon this voltage. Similarly, in analogy to this, how much water this second tank will have will depend upon what is the water level in the first tank itself. But at the same time, apart from this voltage, can you think of something else? The second thing is physical dimensions. For example, now let us introduce a third tank. This is the third tank. You can see I have made the third tank very thin. Now it is physically shorter. Water level will again rise to it in the up to same level. Water will rise to the same level in all the 3 tanks. But the third tank and the second tank will not hold the same amount of charge. Obviously, second has got bigger physical dimensions, so it will hold higher amount of water. The third sphere, being thin, although has got the same level, but will have lesser amount of water. Think that I have connected this battery to a smaller sphere as well. Now, this smaller sphere will also attain a potential of 1 volt as it holds some charge Q dash. Will Q dash be equal to Q? The obvious answer is no, because although their potentials are same, but it has got physically higher dimensions. So that means that it requires more charge to go up to 1 volt potential. And this is a smaller sphere, so its potential will rise very sharply as charge is given to it. So with a very small amount of charge Q dash relative to this, it will also attain the potential V. That means how much charge can we hold on to a conductor or a device depends upon number 1, that is the potential difference applied, and number 2, its physical dimension. And that comes in the form of this constant of proportionality. Let's say call that C as capacitance of this device into V. So C is constant of proportionality, which depends upon physical dimensions and whether it's leave it. The other things like dielectric or conducting behavior, I'm leaving that for the time being. But this primarily depends upon the physical dimension. So this is called capacity of the device, and as you can see, its units are coulomb per volts, or that's also called 1 farad. The capacitance is measured in farads, and 1 farad is equal to 1 coulomb per volt. That means the capacity of a device would be called 1 farad if its potential rises by 1 volt when you give a charge of 1 coulomb to it. Now, what about the dimensions of this capacitance? The dimensional formula, you can find out that very easily. How? Capacitance is basically charge over voltage. Charge is current into time, A1, T1, and voltage or potential difference or EMF, whatever you call that, that's work per unit charge, work done per unit charge. So it is M1 L2 T minus 2 divided by A1 T1. So this A1 T1 goes up there and it becomes A squared T squared divided by M1 L2 T minus 2. This becomes M minus 1 L minus 2 T4 A2. This is the dimensional formula for capacitance. Let's find out the value of capacitance of a spherical conductor. That will give us an idea about how much charge a given device can handle. Let's say I've got a sphere and I gave it charge Q and its potential rises to voltage V. Its capacitance would be Q by V. Let's say its radius is R. Q divided by V is 1 by 4 pi epsilon naught Q by R. You can see Q and Q get cancelled. The capacitance would turn out to be 4 pi epsilon naught R of a spherical conductor. So you go to spherical connector, you want to see how much its capacity is. That's purely dependent upon its radius. And 4 pi epsilon naught is constant. Let's think of a conductor as big as the size of Earth. Consider a conductor of the size of Earth. How much would be its capacity? So I can put R equal to 6400 kilometers, that's the radius of Earth. So you can write it down 6.4 into 10 is about 6 meters approximately. 6400 kilometers, that can be written as 6.4 into 10 is about 6 meters approximately. And let's find out its capacity, the numerical value. You would see C is equal to, we know that 1 by 4 pi epsilon naught is 9 into 10 raised to the power 9. What I want? 4 pi epsilon naught. So it is basically 1 by 9 into 10 raised to the power 9 into 6.4 into 10 raised to the power 6, the value of R. To solve it out, it will turn out to be around 711 microfarads. It's interesting over here. The first point is that even if you have got a capacitor, even if you have a conductor of the size of Earth, even then its capacity is turning out to be of the order of less than 1 millifarad. Had there been 1000 microfarads, that would have been 1 millifarad, so only 700 microfarad. That means it's less than 1 millifarad, rather approximately 0.7 millifarads. So farad is a too big unit to measure capacitance of practical devices. Rather, microfarads, nanofarads, picofarads, 10 is per minus 12 farad, that is, they are more practical way of measuring the capacitance of practical devices. The second point is that just taking a conductor and connecting it to a source of charge to store charge on it is not a very good way of doing the job. That means that simply by connecting it to a battery won't help. It will store very little charge, even if it is of the order of the size of Earth. Even then the conductor will have capacity of the order of microfarads. This is ridiculous. That this is not the right way to store charge. So we'll have to think of something else. And that's where the topic of parallel plate capacitor will come up. That I'll do in the next topic. Thank you.